Hey, good morning, folks. Glad to see many of you showing up at this early morning session. My name is Silvano Coriani, and I'm here together with my colleague Denzil Ribeiro. We are program managers in the Azure SQL team, and the topic for today is, we hope, an interesting one around building software as a service solutions on top of Azure SQL Database. And our agenda for today is to kind of quickly recap, some of the SaaS kind of principles, including the multi-tenancy aspect, which for the data tier is a super important one. And we will go through some of the options that typically we see customers implementing in SaaS solutions for the data tier. And then we will drill into what different flavors in Azure SQL Database can be used to actually host the data layer of our SaaS applications. And we'll drill into some design and management patterns that we've been working with on a number of these SaaS applications. So, as you probably are aware, the SaaS industry itself is actually growing faster than anything else in the IT industry these days, right? So a lot of companies are not doing in-house development anymore. So they are relying on third-party apps, often delivered through the SaaS model, right? And companies building SaaS applications are actually creating the next big wave of application development in the market. And we see this actually on our end, and I will show you some numbers later on how SaaS builders are today using Azure SQL Database as their platform of choice for the data tier. But again, kind of the multi-tenancy aspect, designing a multi-tenant data layer is a challenge today, right? So, and multi-tenancy is a critical aspect for SaaS builders because it's impacting directly their kind of margins and their costs of delivering, their solution, right? So, being the database layer, one of the most quote-unquote expensive components of a solution, because the rich query processing and storage capabilities are actually more expensive than, let's say, a web front-end layer, which is delivering the application pages. It's making this design particularly critical for the success of an application, and specifically for finding the best price and performance point based on what the SaaS solution needs to deliver. Okay, I could, as an ISV, as a SaaS builder, I could, throw a lot of hardware to the problem and make sure that the performance of my application are super great for the users, but then I'm not going to make any money out of that solution typically, right? So I need to find, the right sweet spot between all those dimensions. In the deck, you can find this article of around how our own, one of the major SaaS solutions on top of the Microsoft Cloud, like the Dynamics 365 family of products, have been, transitioning from an on-prem, let's say, environment, on-prem deployment into the cloud, into Microsoft Azure, using Azure SQL Database as a database layer for their solutions. And you will see a lot of details around how, again, those design choices are heavily impacting the success of an application. And again, the key concerns around data management for a SaaS solutions are, as I was saying, costs, but more importantly, the cost projected on a tenant basis, right? The tenant is effectively the user or the organization which stands on the other side of the wire and is using our application, right? And if I have 10 millions of those entities, right? And what is important at the end of the day is the cost that I'm facing in hosting one of those tenants, because typically the business model of a SaaS application will redeliver in a way that cost to their end user, and that cost will impact my margins at the end of the day. The ability to scale, I may start as a small kind of startup, but because my solution is so successful, tomorrow I may need to host hundreds of thousands of successful companies on the other side of the browser, let's say. And so the volume and the amount of traffic, the database traffic that I need to sustain may grow significantly. At the same time, all the SaaS solutions as a multi-tenant solution needs to face the security and isolation problem, right? How can I make sure that data of my different tenants are secured, are compliant, and so on, right? I can put all customer data in the same basket, but then how can I guarantee to customers that, hey, someone else is not looking at my data in that database? And then there are, of course, other considerations like how can I make my database layer reliable? How can I be reliant to disasters and so on? But even more important, pretty much every single SaaS solution is giving their end user the ability to customize a little bit. Things like database schemas or index definitions or such, right? So how can I let a single tenant do some changes in their own kind of database layer without impacting the others, right? So those are the typical problems that a SaaS builder needs to face. And what we are seeing is that there are typically couple of 2-3 patterns that we see implementing SaaS solutions. Normally based on existing applications, right? The one is, hey, I'm just going to clone for each of my tenants a dedicated environment, right? So this is essentially a very expensive option because every customer will get a compute unit, a storage unit, and such. And typically, I have a front end which is kind of redelivering connections to all those kind of back end environments, like that my application is generating. The other option is typically, hey, I'm gonna isolate my tenants' data in a single database, right? So my application tier can be shared, but once my user is connected, I'm gonna dial into a single database, and the tenants' data are only stored there. And then I can take advantage of some of the platform capabilities, like, for example, pooling, using a unique set of resources for a number of databases behind the scenes so that I can balance the costs and isolation, right? And generally, typically, I have a catalog, a database catalog, or a catalog somewhere which is telling the system where a database tenant is actually placed in my database fleet. Okay, and the third model is, generally speaking, real multi-tenant database or data store where all the tenants are sitting in the same database. Sometimes those databases can grow, can grow more than what a single database can sustain. So I may decide to actually split or shard, tenants across multiple databases. And maybe some of them are getting so busy in terms of traffic and so on that I want to give them a dedicated database. So a kind of completely isolated database for a hot tenant or for an important customer of mine, right? And some of them may be, again, leveraging pooling capabilities in the platform so that I don't need to spend, a new amount of money for each tenant that I'm hosting in this pooled solution. So what we have seen so far in Azure SQL DB being a very successful pattern is actually this one, right? So the ability to provide a single database per tenant, per each tenant in my solution, and then adopt resource pooling across many tenants so that I can dilute, the cost of running a tenant together with a number of other databases in the same pool. So this approach typically makes it easier to isolate performance because I can give and govern a certain amount of hardware resources to a single database, right? And that database is not going to impact other databases running in the same pool. I can modify schema for one tenant without impacting the others if my application has this particular need. I can scale it down or up individual tenants depending on their needs. I can actually also move potentially a database out of a pool and make it an isolated database if, again, that customer is super important or is using my application heavily and so on. But all the other maintenance operations like backup, restore, export, import data are easier than an equivalent real multi-tenant schema because, those are effectively separated databases, right? So I can operate on a database pretty much independently. Right? But at the same time, it is making it harder to, for example, minimize costs. Because yes, I can pool those resources, but there's a limit in terms of how many databases I can fit into a single pool. Right? So if I really have what generally are called micro-tenants, so entities or businesses that are only using the application for a few times a week or a few times a month, the minimum cost that I can offer for that database in the pool is higher than what they would like, right? So that's a challenge in this particular deployment. If I have to scale to hundreds of thousands or even millions of databases, managing them at scale is actually, a bit harder if we take that path in terms of database pattern. Okay, but again, what we see today in SQL DB, so those are real numbers, so real databases today in Azure SQL Database. So we actually calculated that more than 50% of the total number of Azure SQL databases today are effectively used in that pattern that I was showing previously, in the database per tenant pattern with elastic pools, right? You see some of the numbers. I deliberately, deleted the names here, but some of our internal and external solutions, third-party customer solutions running on Azure SQL Database are using hundreds of thousands of databases in their database tier, hosting, those tenants in isolated databases that are typically pooled for saving money out of those fleets. And this is, again, giving customers a lot of flexibility because if they have, again, hundreds of thousands of databases, they can store them in pools. Single pool today in Azure SQL DB, 2 vCores can host up to 500 databases, right? Which is a good balance in terms of density and reducing cost, while still providing a good experience for those micro tenants. But the same platform can also scale to very high, very big, single tenant databases with like 80 vCores. We have other customers that are actually implementing that kind of pattern. And SQL DB is offering the ability, the flexibility to essentially host both ends of this spectrum in terms of size, right? But again, at the same time, the more you grow in terms of number of tenants, the more you need to automate, right? The first line in this chart, I can talk about that because that's our own Dynamics 365 internal solution, and these data points are actually public. So today they are hosting more than 3 million databases on SQL Database, right? And they can do that without an army of DBAs because they invested a lot in automation layer, which is deploying and managing the life cycle of those databases, right? I don't know if this data point is true, but they say they have only 2 DBAs taking care of 3 million databases thanks to the automation layer that they created, right? And again, on the other side of the spectrum, for those customers that are instead taking a different path, so packing all the tenants in a single database, this approach of the elastic pool would be too expensive for them, right? It's because the lowest cost that we can offer for individual, independent, isolated databases today, that 500 databases per 2 cores elastic pool, may be unsustainable for them, right? So, finding as I was saying, in this case, they will go with a full multi-tenant database design that Denzil is going to talk about in a second. Right, so again, comparing the two models is relatively easy. This database per tenant isolated approach is good for scaling to few millions databases. We see customers actually doing that, so that is proven to be successful. While going with a true multi-tenant design can scale to potentially billions, right? That depends on your database workload itself. So it is offering a good pricing, but not the lowest possible. But again, we think that the green boxes here are more on that database per tenant model. So that's the one that we typically recommend for customers, unless they have extreme needs in terms of number of tenants to host. So in Azure SQL Database, as I was saying, we typically see two approaches, two best options for hosting those two different database design patterns, right? So for this database per tenant approach, we have the elastic pools capabilities in Azure SQL DB that are, again, giving the ability to customers to define what is the maximum amount of resources assigned to that pool, and to host a number of databases in order to dilute, the cost. The minimum cost per tenant that we can offer today in Azure SQL DB is basically 88 cents per tenant per month, or per database per month, if you will, right? And this, you can achieve this using the DTU model and hosting 500 databases in a 200 DTU pool, which is equivalent essentially to 2 cores behind the scenes. On the other hand, if you take instead the true multi-tenant database design, we think that our hyperscale offer is the right one for scaling potentially to billions of tenants in a single database. We can scale up to 128 vCores and 100 terabytes of size. And we recently announced the serverless option for hyperscale, which means that compute portion of the database can actually adapt to the amount of workload. So if you select this option and you have like a set of hot tenants, the database will autoscale potentially to the maximum amount of cores available in that box, and then can shrink down in order to save you money, right? So we think that this elasticity for serverless database fits very well with those SaaS patterns for multi-tenant database designs. Okay, now Denzil is going to talk about how, again, hyperscale is the best fit for this particular design.
Thank you, Silvano. And while we talk about hyperscale, today being kind of the multi-tenants per DB, you could foresee a future where we do have pooling, which we don't have today on hyperscale, right? So what is hyperscale? It's the cloud-native architecture for SQL, where we have separation of compute and storage. We solve some of the VLB problems, and one scales independent of the other. So removing that, remove some of the limits we have with other tiers, right? So if we look at kind of this hyperscale architecture, we have an auto-scaling storage layer, which starts in 10 GB chunks and allocates storage and grows up to 100 terabytes, right? So you don't have to manage kind of the storage layer. There's no limits like some of the other tiers, and it grows as you need. And then you have two compute choices. You have provisioned, which the minimum is 2 cores to 128 vCores. And provision scaling also, because of separation of compute and storage, is in constant time. So you can look at scaling up or scaling down being 10 seconds of downtime, a minute in time, in total elapsed time, if you will. And then you have the serverless option, which is more of usage-based billing. And that's kind of auto-scaling of CPU and memory and some of the caches in the architecture based on application demands. right? And so in this multi-tenant architecture also, we can talk about security, but when you have multiple tenants in the database, you can use the native engine features like row-level security and such to protect data so that a tenant can see only his data. So you'd have a row-level security on a tenant ID, which filters rows for that tenant as your application actually reads data, for that tenant. As the application grows bigger, if you're talking about multi-tenant within a database and that's the pattern you want to go, if you need high availability, we have the ability to add replicas with HA replicas. If you need, we have new things called memory optimized service objectives too. We announced premium series for Hyperscale, where if you need more memory per core, we have an option which is memory optimized, which gives you double the memory per core at a price premium. And then we have the cross-region continuity with GODR, right? So if you need regional resiliency for compliance and things of that nature, we have GODR that handles, geo-replication that handles that to a region of choice. And then if the app needs to scale out, say your pattern is such that you have a few writes and a lot of read API type of calls as part of your SaaS patterns, you have the option of actually, scaling out reads to the HA replica or to the set of named replicas. And the named replicas are within regions. They can be isolated compute units also on a different logical server with different security. If you need to isolate for specific tenants, they share the same storage, but they're read-only. So only your reads can scale out in kind of that way, right? So you can have up to 30 replicas and use them in conjunction with GODR as well. So kind of this is Hyperscale at a nutshell, right? So if we look at architecture, I don't know how many of you are familiar with the Hyperscale architecture? No? So we'll just quickly look at the architecture because it's a little different, than other tiers or single SQL Server. So you have this compute layer. Everything in this blue box is actually connection endpoints to an application. Everything below is Microsoft management. An application connects to a database. The database has main memory and has a layer of SSD cache. And this is for performance reasons, right? All the writes go to an externalized log service. So you never write to kind of storage directly. All the writes flow to this externalized log service. And it's the job of this log service to send these writes to the storage layer and to all the replicas in the system. Right, so all writes, this compute never writes to this. So if you think about it, some of the compute is actually saved on your primary database because it's not doing things like checkpoint and flushing writes to disk or doing any of the backups. All the backups and things of that nature are done by this storage layer called page servers. And this is auto-allocated for you as your database grows. There are 128 chunks of data. You can look at page servers as a chunk of your database. If you have a terabyte, you have 8 of them. Each of them hosts like 128 gigs of data. But this allocated in 10 gigs as you need it, right? And so this log service then, as you insert update data, passes that data to the page server layers. And that data tier is caught up with all the changes, if you will. And then there's durable storage, which is Azure Blob Storage, which is for retention. Or if you have to restore another copy, we actually do that from Azure Storage. Similarly, backups are actually snapshots of this Azure Storage. So backups are never taken on compute. So you're saving precious resources on compute to service more of your workload. And also what that means is because it's snapshots, 100 terabyte backup is almost instantaneous. 100 terabyte restore is 20 minutes, right? Like it's the time to provision your compute. It's not linear, it's a constant time restore. And then you have redundancy at every layer, so all page servers have a replica, the blobs have a replica, so on and so forth, right? And then log service also offloads log based on your retention for restore capabilities. Last but not the least, you have 2 ways to scale out reads. You have this concept of HA replicas. HA replicas can fail over if you have a failure on primary. You can also load balance all your read calls across these HA replicas, so it automatically load balances kind of your read calls. And there is another concept for Redscale called named replicas. If you want to isolate a particular tenant, you can have it to be different cores than the primary compute. You can have it on a different logical server with different security. So that gives you some options, to play around on this stuff, right? So that's kind of the hyperscale architecture in a nutshell. Now we've introduced serverless to hyperscale. Before it was provision. And these are serverless tenants, and I'll point out what is in hyperscale and what is not. So one of the tenets of serverless is autoscaling. So you scale between a min and max of vcores and memory, and they're independent of replicas, right? So if you have serverless on one replica, for example, that replica is only built for the workload coming to it. If the other replica doesn't get workload, it's going to be built at min vcores, right? Then there's the concept of auto pause delay, which isn't yet in hyperscale but exists in general purpose, and we'll look at kind of the parity gap. So that means if the database is doing nothing, it's paused. So all you're paying for is storage. You don't pay for compute at all. If there's no activity for the period that you have defined as inactive period, you're not paying for it at all. Billing is per second. Provisioned is per hour, so you pay only for the resources you use per second. And then it's best, of course, for an intermittent package usage. You don't save if you're always using at peak usage or above average. Above 50% all the time, you're not going to save on serverless versus provision, right? But it allows you to spike up and spike down pretty well. And then you get all the PaaS management benefits, if you will. So one of the differentiated things about serverless, so if you think about provision, your scaling is really of memory and cores is linear. You get amount of memory per core, and if you want more memory, you have to scale up to the next core level. Serverless allows you to, if you need more memory, you can scale up. So you have low cores and have a higher need for memory, or you have a higher need for cores with lower memory because each of them are built as components of the serverless tier, if you will, right? So you can scale up independently. Scale up is typically sub-second, right? And it's almost instantaneously, no break in connections. Most of the time at the high P90 percentiles, we don't have any break in connections. There can be an odd case where you're moved to another node. If you're scaling, for example, from 20 vcores to 80 vcores, we might not have space on the node and we might move over. But for most cases, it's instantaneous and you don't have a break-in connection. So don't even need to, of course your apps still need retry logic for the other stuff that exists, but it's not a break-in connections. And like we said, for provision, you would actually have to double the cores if you wanted just memory or so on and so forth. It's more of a linear scale, right? So what does these do together, if you will? So we offer right now, auto-scaling in preview at least, we offer auto-scaling up to 80 vcores. We will go up when we GA to 128 vcores, which is the premium series, right? We offer auto-scaling independence on primary and HA replica. So if HA replica doesn't get any workload, it is billed at the minimum. If primary gets more workload, it is billed at whatever it gets. Auto-scaling of CPU and memory independently. Of course, hyperscale as a tier itself has a higher performance profile than general purpose. For example, where Silvano was talking about packing 500 databases in a pool. You have business continuity and price optimization. So it's effectively great for databases that burst. You can burst almost instantly, from that perspective. And I'll show you one quick aspect of, I think it is, is this one. So this is an example where, we can burst instantly, right? So you see CPU percentage, and I'm going to add another variable called add metric, where's the add metric? Called memory. Okay, so we have two metrics here, CPU and memory. And I'm just looking, I just ran a workload literally. You can see that there were no resources consumed here, or min resources consumed here. And this is a 2 to 16 core, and we burst up quickly. Burst was instantaneously achieved, right? We didn't have a lag. The workload came up. The burst was almost instantaneously. If you look at billing, and these are non-correlated chart, but if you see the cross point, billing spikes up at the same time that resource usage bursts. And the last thing I will show you in billing is if I have this HA replica which is also defined. You see, when the resources are almost zero, you're billed at the minimum CPUs. When the resources spike up, you're billed at whatever resource you're using. And then the orange line is this HA replica, which I added around this time. We are not doing any read scale out, so it's using minimum cores to redo the log that we are actually applying to primary. It's using the minimum billing there because it's there just for HA reason. It's not actually accepting incoming workload. So that's kind of how billing will help. I'll hand it back to Silvano. And like I said, today we don't have the pooling aspect, but you can think of a future that we will. Thank you, Silvano.
Thanks, Denzil. And just to kind of summarize, so for hyperscale, actually for true multi-tenant database designs with unpredictable workload and potentially millions or even billions of individuals or companies or entities that are hitting my database, hyperscale serverless is definitely the right choice because it can give me that elasticity, that cost control, and at the same time, the ability to scale up to hundreds of terabytes so that, we have no kind of concerns in terms of being able to grow our business. On the other side of the spectrum, the elastic pools in Azure SQL are basically giving us, as I was saying, a cost-effective solution for managing strong isolation between tenants. So all the tenants' data will get separated in their own, databases, right? And pools can help us to spread, the cost of running those tenants across, effectively multiple databases and multiple customers. Individual pools can scale from 2 to 128 vCores, and again can host up to 500 databases. So you can still find your own sweet spot in terms of performance and costs, and then you can divide and manage. All your tenants, the more you grow in terms of, your business across multiple elastic pools in order to manage your fleet. And this can be a constant growth. You don't need to pre-allocate, all the resources in a single time. You start filling up pools, and then you add more pools the more you need that, right? And this is, again, pools are a great solution for those unpredictable kind of workloads because I can have a group of tenants, each of them can be active at a different kind of point in time, right? And what the pool is giving me is effectively, giving me the ability to share, utilization across those databases, depending on what type of workload I have. I may have a steady state workload across all the tenants, but still have tenants that are spiking up and down, during their utilization. I can have daily profiles, usage profiles that are, for example, busier during business hours and they go down, in the evening and such, or they can have kind of weekly spikes and such. And elastic pools are actually giving me the ability to, with a predictable amount of resources that I'm assigning and cost that I'm assigning to that group of tenants to go and manage and distribute the cost across them, right? What we see effectively, sorry, is that if we do some sort of capacity planning and we organize our pool, this is an example of a 1 vCore pool hosting 385 databases. We see that individual databases are going up and down, but the total amount of utilization for the pool is still under control, so we have room for even more tenants in this kind of shared environment, right? So my application, my SaaS application, can actually manage, kind of a progressive growth by, asking the Azure SQL control plane to create a new pool for me when a new tenant is coming, to start potentially also pre-allocating databases and assign them to a new tenant which is registering, a new customer which is registering in my SaaS platform, and having immediately available that database, so no need for waiting even few tens of seconds before the database is ready. And then the application will start using and start adding new databases in the pool at no cost. I mean, adding new databases in the same pool is not going to cost you more, right? Because the pool is the unit of allocation, resource allocation. So the more you need, because you are successfully onboarding more and more customers, the more pools you can deploy. And then when a pool is getting too busy, you can extend it if you like, because you can still manage elasticity at the pool level, or you can, for example, move a database away to another pool if you want to offload some of the workload to that one, right? So, and if you really need, again, if you have a very successful customer, you can always move it out of a pool and give him a dedicated database without disrupting, the application workload to that database. This is a pure online operation, and the user is not going to even notice that has been moved out. So my kind of automation layer, as I was saying, can take care of this, right? And I'm just giving you an example of what the Dynamics team is doing here. Again, this is all public per that blog post that I was referring you. So they have this automation layer where what they are doing is they are dynamically allocating databases, new databases to pools, right? And looking at what pools are hot and which one are cold, so that they can deploy databases, creating new pools where it's needed. But if a given pool gets hot because they have a very busy tenant over there, they can actually rebalance resources across pools, so that those active tenants can actually have all the resources they need in their pool and don't need to actually suffer from a resource perspective, right? So from an application development perspective, what this automation layer needs to do is effectively to deal with the provisioning of databases in those pools and implement what we call data-dependent routing logic in the application. So reading in the tenant catalog which database belongs to my tenant, and effectively, once that is onboarded, is just connecting, reading from the catalog where the database is, and then the application from there can just connect, to its own database. This is really simple. I will show you in a second a demo solution that we have on GitHub that you can actually take as an example on how to build, this logic in your application. And again, we also have capabilities like Elastic Jobs, because the moment you have multiple databases hosting your tenants, what if I need to run a task across all of these databases? So we have a concept called Elastic Jobs in Azure SQL DB, where you can define your jobs, right? Like T-SQL scripts, adding a column to a given table, or doing some maintenance. And then you can actually execute those commands across a number of tenant databases in your fleet, right? And if you also need, for example, to extract information from all those tenants, you can actually do the same. You can do analytics, for example, across all your tenants' data, and you can have a job in Elastic Jobs which is collecting analytical data from your tenants and pushing to, for example, a dedicated database where you run analysis and such. This can be in SQL DB, can be in Azure Synapse or somewhere else, right? And then your Power BI users or Excel users can analyze, for example, the usage of all your tenant databases and such. Right, so again, I was referring to this Wingtip Tickets demo app. You can find it on GitHub. Those are the links that you will find in the slides. And there's also a nice tutorial online that is guiding you through all these different patterns, right, for designing your database layer in a SaaS application. Okay, so I'm going to show you some of those patterns and capabilities in a second, right? So what the Wingtip sample app is providing is a pretty complete set of capabilities from deploying your tenant databases, registering your tenants in a catalog, connecting the application to each kind of tenant's data, monitoring the application, alerting. There's also a nice workload generation set of scripts that I will show you in a second that are actually demonstrating you how concepts like elastic pools can help you to define and manage the resource and the performance experience that your tenants are going to have with those different multi-tenant patterns hosted in Azure SQL DB. Right, so it's a pretty rich demo app. I'm going to now show you some of these capabilities, right? So this is a dashboard representing a database per tenant deployment, right? You can get that deployment from GitHub. As I was saying, there is this Wingtip Tickets SaaS database per tenant repo, right? Where again, this pattern is represented. You have a deploy to Azure button here. You click on this, and in like 5 minutes, I'm going to just show you the template here, which is deploying everything. Is deploying. Here we are. Is deploying your SQL Server Logical Server. So sorry, Azure SQL Logical Server is deploying your web app. Is deploying everything for you. You just click deploy here, and you will get a running environment, right? And this is exactly demonstrating the idea of elastic pools for this database per tenant scenario. So you see below the resource utilization of my pool, right? So you can see that is going up and down depending on each individual tenant workload. And on the top chart, you see independent tenants utilization, right? This app is representing a ticketing SaaS platform that is used by a number of venues like sports centers or music concert halls and so on. So each tenant represents a different venue, and you can see there are right now around 20 different tenants in this single elastic pool. Is a very small elastic pool, 50 DTU. So this is probably going to cost you like, I don't know, a few cents per day per tenant per month in this particular setup. And I have a background job which is hitting all those databases with new ticket registrations for attendees of those kind of venues events, right? So this is exactly the pattern that we think elastic pools can help you to achieve. And as Denzil was saying previously, for Hyperscale, with the potential future kind of addition of a pooling mechanism, right? You can think about, so today we have pools that you statically define in terms of minimum and maximum amount of core, right? But in the future, you can think about a similar serverless experience also for pools, right? We have serverless for Hyperscale, we have pools for Hyperscale, and in the future we think we can do the serverless pooling mechanism that will give you the ability to again scale up and down single kind of pools for a number of databases within that, right? I have a similar dashboard here for an equivalent multi-tenant scenario. So this is using Hyperscale serverless, right, in a similar fashion to the as a setup, but this is a true kind of multi-tenant design. What does it? This means that all those venues are stored in the single database, and of course the database design is going to be a little different because our tickets, quote unquote, here will have our tickets table will have a venue ID, right? So having a true multi-tenant design means that all your tables, especially the transactional tables, will need to have that tenant ID column, and all the data will be stored in the same basket, right? If we take a look at the code for those two sessions, so again, when you clone that repo, you will get everything from your application code, ASP.NET code and such, and all, database projects, everything you need to start looking into those patterns, right? And this is the database per tenant repo. So it's demonstrating this elastic pool pattern that I was referring to. If we look at the tenant database schema design here, you see that the tickets table, which is the most important one, right, is basically representing, tickets and the business that my application is actually running. It doesn't require to have a venue ID, right? So a tenant ID in the schema, because we know that in this database, data will get isolated at the tenant level. There's no sharing from a database perspective. If instead I look at the equivalent, and I need to pick up the right window here. This is the multi-tenant schema. For the same tickets table, we see that there is this venue ID column that represents that particular tenant key or tenant ID. So we need to design our database differently. And as Denzil was saying, we can actually take advantage of, let me see if I can find that. There were some, yeah, do you see that? I was trying to find the right file representing the, but anyway, there are some row-level security functions that are implemented in this particular database that can help to make sure that when my application is connecting to the database and is basically passing a tenant ID, those queries that I'm going to execute against the database will get the where clause appended with tenant ID equal, and then the rows will get filtered for me by the database engine itself, so that I may not require specific checks at the application level, right? So it's a way to kind of simplify the application development in talking to a multi-tenant database design like this, right? Again, two ends of the spectrum. The fully isolated tenant design, you go with a lot of smaller databases organized in pools, and you can actually provide that separation and that isolation that can help in a number of scenarios. But if you really want to have super high density in your database, namely billions of potential customers, like in a typical business to consumer scenario where your tenants are individuals with their own phone and doing some transactions a day or a month or whatever, some operations randomly. This kind of true multi-tenant design and the usage of hyperscale serverless are going to cover that end of the spectrum in terms of costs and in terms of performance. So, yeah, as we are really interested in talking to customers and to SaaS builders that are building solutions with those kind of patterns in mind. So if you are in this situation, please come talk to us. Sorry. You can expect some news coming from the Azure SQL platform, trying to simplify the implementation of those patterns in our platform. So again, please talk to us. But in the meantime, if you have questions around the different options that we showed, please go ahead and ask now, or you can pick up you can ping us later on at the booth or everywhere. So is there any question? No questions. Okay, in the deck you will find a number of other references and useful kind of informations and blog posts and tutorials for implementing those multi-tenant solutions. If there are no questions, I think we are almost on time. So if not, again, thanks a lot, folks, for attending, and talk to you and have a great conference.